Let's now look at an example where we're taking a system that starts out as unstable, and by providing frequency compensation, we can make the system stable. So we're going to consider a 3-pole amplifier with a loop gain function as given in equation 1. So we notice we have 3 corner frequencies. We have 10 to the 4th, 10 to the 6th, and 10 to the 8th. So we're going to say we assume that these are far enough apart so that they're not really interacting. And so that's going to be useful as we're doing a certain part. What we're trying to do is we want to insert a dominant pole so that our phase margin is at least 45 degrees. And we're making the assumption that by inserting this dominant pole, we're not changing any of the original 3 poles. Okay, so the basic process, of course, is what we're doing is we're inserting some dominant pole. And so we're going to say we're inserting this pole at some frequency, F equals F sub P D, pole dominant. And what that's going to do is it's going to be adding a term to our equation above. So it adds the term 1 plus J times the quantity of F divided by F sub P D in the denominator of equation 1 above. And so basically all that is we're going to add another term right here. Okay, so now what we want to say is we have this requirement that we want the phase margin to be at least 45 degrees. So we have to go back and say, well, what does that mean? So we said a phase margin of 45 degrees means that at a phase angle of negative 135 degrees, so 45 above our negative 180, we should have the magnitude of our function, and just in terms of f here, equal to 1. So we want this condition to be true here for a phase margin of 45 degrees. So what we're going to assume is we can assume that this dominant pole frequency is much less than our first corner frequency. So assume this F sub PD is much less than the 10 to the 4th, which is the lowest of our 3 corner frequencies highlighted here. And based on that, what we can say is we can say that our phase angle is approximately negative 135 degrees at that first corner frequency, which is 10 to the 4th hertz. And so we went through the reasoning for that with our previous example when we were designing on phase margin. If you're looking in the notes, that's on page 4-35. Okay, so now we know sort of the frequency that we're going to be checking. We want at this frequency for our phase to be negative 135 and our magnitude to be 1. So let's write our equation for our magnitude here, and then we can use that information to solve for the frequency of this dominant pole. So our magnitude of our loop gain function is, we want it to be equal to 1, and what we can set that equal to is we're going to have a term from our dominant pole that we're inserting, so 1 plus our F, and remember our frequency that we're using is this 10 to the 4th, so we have 10 to the 4th divided by F sub PD, that quantity squared, and then we're going to have a term for each of our other original 3 poles, which we're assuming are unchanged, so 1 plus, again, the frequency we're evaluating at is 10 to the 4th, divided by 10 to the 4th, quantity squared, and then we have 2 more, so 1 plus frequency that we're evaluating, 10 to the 4th, divided by 10 to the 6th, quantity squared, and then for our third original pole, now our 4th pole, we have 10 to the 4th, the frequency we're evaluating at, divided by 10 to the 8th, quantity squared, and then on our numerator, we just have the 1000. So of course what we can do is we can solve for these other numbers, and I'm going to write them out so we can see sort of the contribution from each of these poles. But of course we just have this first term here is sort of coming along because that has our unknown value in that, so FPD squared. And then from our second term, we have 1.414, and then each of our other two poles, we just have 1. And so what we can do is we can solve that for FPD, so that's one equation, one unknown, and we get that our FPD is approximately 14.142 hertz. So of course, depending on how much control we have over that, we might just be able to say 14 hertz is the closest we can get. And so keep in mind then that satisfies this assumption that we set up here that our FPD is much less than 10 to the fourth. And so ultimately what we've said then is if we come to this system and we are able to add a pole with a frequency of 15 hertz, then our system will become stable and it will have a phase margin of 45 degrees.